Good morning, everyone. In this work, we investigate the structural and morphological evolution of the zinc, molybdenum, and oxime system by systematically change the zinc to molybdenum precursor ratio and comparing two different synthesis methods, hydrothermal synthesis and homogeneous precipitation. The main objective was to understand how the variation in the zinc and molybdenum ratio affects the formation of the oxide of zinc, oxide of zinc molybdenum, and oxide of molybdenum, and secondary crystalline phase, as well as their corresponding morphologies. For the hydrothermal route, zinc nitrate and ammonium molybdenum were used as zinc and molybdenum precursor respectively. The precursor solution were mixed according to different zinc and molybdenum molar ratios from the zinc-rich to molybdenum-rich composition. The resulting suspension were tried the hydrothermal at 114 degrees Celsius for 10 hours after the reaction. After the reaction, the products were washed, dried, and calcined at 500 degrees Celsius for 2 hours. The second method was homogeneous precipitation in case zinc nitrate or ammonium molybdenum was combined with the urea as the precipitant agent. The solution were heated to the 95 degrees Celsius, allowing the gradual decomposition of the urea and the conquest increase in pH, which permitted precipitation. After precipitation, the samples were dry and calcined under the same final temperature conditions. Therefore, both methods were evaluated using the same general zinc-molybdenum compositional sequence, allowing us to compare not only the effect composition but also the effect of the synthesis route. The X-ray diffraction results revealed a clear structural evolution of the molybdenum content increase. For the homogeneous precipitation samples, HP1 consists mainly of the Wursita zinc oxidum. When the molybdenum is introduced as in HP2, the zinc oxidum coexists with the alpha zinc molybdenum, indicate the beginning of the reaction between the zinc and molybdenum containing space. The most important resultant is observed for the HP3, where alpha zinc molybdenum becomes the main crystalline phase with no significant diffraction peaks associated with the zinc oxide or oxidal molybdenum. This suggests that the 1-to-1 precursor ratio provides a favorable composition for the formation of the oxidal molybdenum zinc. When the molybdenum content in the further increase as in the HP4 alpha oxidum molybdenum begins to appear together with the alpha zinc molybdenum oxidum. Finally, HP5 contains predominantly alpha oxidum molybdenum. The behavior can therefore be summarized as a progressive transformation from the oxide zinc through zinc molybdenum towards oxide molybdenum as the molybdenum concentration increases. However, the hydrothermal route shows a more complex phase evolution. HT1 is mainly composed of the Forsita zinc oxidant. In HT2, an additional zinc molybdenum hydroxide related phase is detected. For HT3, oxide is still the dominant phase, but the alpha zinc molybdenum begins to develop. In HT4, alpha zinc molybdenum becomes the predominant phase, although additional phases such as the penta-5 sodium molybdenum 6 and the 3 zinc 2 molybdenum are also detected. Finally, HT5 no longer contains the molybdenum related phase in this and instead show alpha 3 oxidal molybdenum together with the molybdenum sodium. The results demonstrate that the hydrothermal method produces a more complex phase evolution with the can be associated with the chemical environment generated during the hydrothermal reaction. The effective area results support the X-ray diffraction observation in the molybdenum contained samples but associated with the molybdenum oxide and molybdenum oxide molybdenum vibration become progressively more evident as the molybdenum content increase. In addition, the zinc oxide vibration associated with the zinc oxidon and zinc oxide molybdenum can be distinguished in the low Weber number region. For the hydrothermal samples, additional bands related to absorbed space and surface carbonate space are absorbed, particularly in the molybdenum-rich samples. Overall, FTR confers the progressive modification of the metal-oxide bonding environment as the zinc-molybdenum ratio changes. The CEM scanning electron microscopy analysis reveals the structural changes observed by X-ray diffraction are also accompanied by significant morphology evolution. For the homogeneous precipitation road, HP1 represents an irregular and highly aggregate morphology, which can be associated with the particle growth and the agglomeration during precipitation and subsequent thermal treatment. With the incorporation of the molybdenum plate-like structure behind to apart in HEP2, this structure becomes more evident in HEP3, where molybdenum zinc is dominant crystalline phase. When the molybdenum content is further increased, the morphology changes again, showing irregular cluster, and in the molybdenum-rich samples, lamellar or flag-like structure associated with the oxidum molybdenum. The hydrothermal samples show a different morphologic evolution. HT1 exhibits a clear nanorod morphology, characteristic of the anisotropic growth of the zinc oxidon. As the molybdenum is introduced, these nanorods coexist with the development of plate-like structures. For HT3, the formation of the zinc molybdenum is accompanied with a more pronounced lamellar morphology, while the remaining rod-like structures are still observed. At higher molybdenum concentration, lager laminar structure and additional granular or cluster morphologies appear consistent with the formation of the secondary phase detected by the X-ray diffraction. Finally, HT5 exhibits a predominantly flat-like structure associated with the molybdenum oxide rich composition. In conclusion, both the synthesis methods demonstrate the clay composition dependent evolution of the zinc molybdenum oxidant system. Increasing the molybdenum content promotes a transition from the zinc oxidant toward zinc molybdenum and eventually toward oxidum molybdenum phase. However, the synthesis method also strongly influenced the evolution of homogeneous precipitation favors a more direct transition toward alpha zinc molybdenum, with the HP3 showing the most representative molybdenum zinc composition. In contrast, the hydrothermal route produces a more complex phase evolution, including an additional molybdenum-contained phase. These structural changes are accompanied by significant variation in the coral size, microstain, and morphology, demonstrating that the zinc-molybdenum ratio and the synthesis rate are key parameters for controlling the final properties of the zinc-molybdenum oxidation system. Thank you for attention.